Now we've talked about the first order circuits. Now we want to talk about a second order circuit. A second order circuits contain two storage elements. For the first order circuits, we've been dealing with just one storage element. But in the second order circuit, we have two storage elements. And these two storage elements are going to be of different type, or they could be of the same type, but not in parallel or in series. So they could be connected anyhow, but not parallel or series. Okay. Total response is still the sum of natural and forced response, just like we have been doing before now. So you find the natural response, find the forced response, add them together to get your total response. Okay. So the procedure pretty much is the same, except that there are some variations I'm going to show you right now. The natural response of the RLC circuit, in this particular case, when we have two storage elements, we're talking about the L and the C. Okay, so when we now have our resistance added to it, we have the RLC. So the natural response of RLC circuit may consist of functions other than the decaying exponentials. Okay, for the simple RL and RC circuit, we had just decaying, exponentials, but for the RLC, we may have more functions than that in addition to these. Okay, so we'll look at all of those as we go on. To solve a second order circuit, two initial conditions are required. Why do we require two initial conditions? Because at the end of the day, we are going to obtain a characteristic equation that is of a quadratic nature at the end of the day. So in that particular case, you can say that we would obtain two initial conditions, but then we need two initial conditions. So that simply means whenever they are giving you questions, they will give you the initial condition for the current and voltage, or for inductor and capacitor. Okay, you will see that as we go on now. All right, so this is the format this is going to take. You can see that we do have the first order circuit in this format. If you remember, our first order circuit is what it looks like, and then we'll see the total response will be the natural response plus the forced response. Okay, this is what we said. And remember, then we said that you say that xn will be equal to e exponential k, all right, exponential st. All right, that's what we used to do. That's what we do for first order circuits. And then if you also remember, we usually say that let the first function or the first term be equal to an arbitrary constant a if the first term is a constant. Okay, this is what we used to do to find the natural response and the forced response, and then whatever we obtain, we add them together and so on. All right, this is what we did with the first order circuits. Then the second order circuits, they are represented by this kind of function. Like I told you, we'll be dealing with quadratic function. Okay, so you can see the second order term, the first order term, and the constant, the linear term, and then the constant term. So a similar procedure as before is applicable here. First of all, we find the homogeneous equation, which is going to represent the characteristic equation. All right, so what you find here is that the first term, you ignore it when you want to find the characteristic equation or homogeneous equation. So that means you equate everything to be equal to 0 because you're not dealing with the first term. And after that, you find the first equation. To find the first equation, you equate the entire equation to the first term. And at the end of the day, you get your on first solution, you will get it, which is going to be the xn of t. And then you also get your first solution, which is going to be the xf, okay, of t. At the end of the day, when you add both of them together, you get your total response. You superimpose both of them, so you have a superposition. So you have this correct, writing x here, it becomes xn plus xf, and then the story goes on, the explanation and analysis goes on, and you obtain something like this at the end of the day. This gives you an idea of what we'll be dealing with as soon as we start solving some problems. But before then, let me just quickly take you through a couple of other important things. Okay, for natural response, how do you deal with it? Don't forget, I told you we're going to have a natural response. Okay, so this is going to represent the natural response, and this is going to represent the forced response. So first of all, let us deal with the natural response. Consider the homogeneous equation that we have here. This is the homogeneous equation. So you take your xn of t equal to k exponential st. You know, you're familiar with this already as a trial solution. If you substitute these into this particular equation, you're going to obtain these: k exponential st s squared plus a1 s plus a0 equal to 0. In the case of the first order, you're going to just have k exponential st into bracket s plus the constant equals 0. Okay, so that's what you're going to have here. In this particular case, this is going to either be 0 or this is going to be equated to 0. Well, you know your k exponential st cannot be equal to 0, right? That means all we have left is going to be this s squared plus a1s plus a naught equal to 0. By definition, KEST is not going to be equal to 0. So when you have s squared plus a1s plus a naught equal to 0, leave that your equation 1. You can go ahead and solve these. Okay, to solve these, okay, given the nature of what we do have here, you're going to use the quadratic formula or quadratic equation to solve these. If you do that, you obtain s1 equal to these, and then you obtain two natural solutions, two important natural solutions. So you obtain xn1 will be equal to k1 e s1t, xn2 will be equal to k2 e exponential s2t. Okay, so because normally when you solve a quadratic equation, you would obtain two solutions. Okay, so that is why this is the way it is here. All right. So instead of getting one single natural solution or natural response, we get two natural responses. Two distinct solutions individually form a solution. For a linear equation, any linear combination is also a solution. So if you add these two together, it is also a solution. Okay, so for some of you who have done linear differential equations before, okay, so this is mathematics. So when you have two solutions, any linear combination of the two solutions will also be a solution to the differential equation, linear differential equation that we have. So xn equal to xn1 plus xn2 would also be a solution. So as xn1 is a solution, xn2 solution, xn is of course also a solution. So if we write the equation 1, if we write it as x squared plus 2. Now there is a new term we are introducing here by definition. It is called zeta, right? We have our beta. You know what beta is? We have our gamma, we have our lambda, we have all of those. We also have these, which is called zeta here. By definition, if we write these as s squared plus 2 zeta w naught s plus w naught squared equals 0. Okay, it simply means that we are replacing a1 with 2 zeta w naught. That's what it simply means. If you compare these with equation 1, we are replacing these two. So we are saying that a1 is equal to 2 zeta w naught. Okay, also from here we are replacing a naught with w naught squared. So we're saying that a naught is equal to w naught squared. All right, if we do that, you can say that from here our w naught squared would be equal to square root of a naught, and that is exactly what we have here. And then you can say that zeta will be equal to a1 divided by 2 root a naught. Okay, because this represents w naught. Normally it will be zeta equal to a1 over 2 w naught. Okay, so and w naught will be equal to square root of that, square root of a naught. Now you will see that we are introducing some terms here. We have the undamped natural frequency, and then we have the damping ratio and undamped natural frequency. Damping something would mean that you are trying to, it's a term used to define a situation where you cut off the sources. It's a term used to define a situation where you cut off the sources and then your response gradually tilts towards 0. Okay, so when you have an oscillation, and in terms of frequency, now because we're introducing frequency terms here and W naught and all of those. So you have an oscillation and then you cut off the source of the oscillation. Okay, damping is a term used to define a situation whereby the oscillation gradually stops, slows down. Okay, probably if you have an oscillation that is this high, probably you have, let's say you have an oscillation that is high like this. So when you cut off the source, the oscillation gradually slows down, becomes small until it becomes 0 at the end of the day. So that is how we define damping in the real sense of it. Okay, so having that in mind, it simply means that the characteristic exponents S1, the solutions that we are bringing here for the natural solution can then be given as minus zeta plus or minus square root of zeta squared minus 1 W naught. Okay, so what you would find here is that we just did some rearrangement here. That's what we did here. So when we talk about damping situations, we could have an overdamped situation. When we have an overdamped situation, okay, what we usually have is that zeta is usually greater than 1 when we have an overdamped situation, all right? And when zeta is equal to 1, what do we have? When this is equal to 1, we have a critically damped situation. So this is overdamped situation, okay? This is overdamped situation. This is going to be critically damped situation when zeta is equal to 1. You could have a situation where zeta is actually less than 1. In that particular case, what you have is an underdamped situation. And then we could have a situation where zeta is equal to 0. Okay, so when zeta is equal to 0, we have undamped situations. This is underdamped, this is undamped, this is critically damped, and then this is overdamped situation. Okay, so these are 4 types of situations you can have an oscillating term that is being damped. These are the kind of scenarios, different scenarios that you can have. All right, so having this in mind, let's go ahead and then discuss the 3 scenarios that are important for our work. 3 most important cases that we can discuss for the general solution. All right. Now we want to talk about 3 cases for the general solution. We have an overdamped case, and I told you that whenever we have an overdamped case, it simply means that zeta is greater than 1. In that particular case, you obtain real and distinct solutions. Please pay attention to this. You obtain real and distinct solutions. So we have, when you have a real and distinct root after solving the quadratic equation for S1 and S2, okay, so you can say S1 is equal to gamma 1 is equal to this, and this is equal to gamma 2. So these are 2 real and distinct roots. The natural response is usually given as K1 exponential gamma 1t plus K2 exponential gamma 2t. This is very important so that we know how to deal with cases where we find the homogeneous equation. We obtain 2 solutions where both of them are real and distinct. Okay, so they are different from one another, not the same, and then they are real. Okay, not complex. So for circuit with passive elements, driven by independent sources, gamma 1 and gamma 2 cannot be positive. Okay, so that simply means S1 and S2 must be negative. For circuits with passive elements driven by independent sources, gamma 1 and gamma 2 were positive. I have about 1 or 2 examples to show you to explain that to you, or to buttress that point. With independent sources killed, what this simply means is that the energy stored cannot increase beyond the initial stored energy. When you kill the sources, it simply means that the energy you have stored will not increase anymore. When you have a damped situation, it simply means probably the oscillation will start reducing gradually, start going down until it stops eventually. And this happens when you kill the sources in a circuit. And that is why, it is safe to assume that the solutions cannot be positive. The natural response just keeps reducing, it keeps going down and going down and going down, all right? Overdamped case is when there is sufficient damping for each term in the natural response to steadily decay to 0. In lightly damped case, the damping may have some oscillations, okay, but in overdamped case, there is enough damping to ensure that each of the terms we have in the natural response steadily decay to 0, as you can see in the case of this oscillation like this. Okay, so all of these are important. They are theories that you just need to be able to buttress what we're talking about. Then we have a second case where we have the underdamped case. In the underdamped case, it simply means zeta is less than 1. And don't forget, I told you, when zeta is less than 1, we are talking about the underdamped situation. So it simply means that in this case, S1 and S2, when you solve the natural response equation that we have, when you solve them, you will obtain complex conjugates. Okay, so the solution would be the same, but definitely the only thing that will be different will just be the sign when you solve them. Okay, so they are called complex conjugates, and W cannot be equal to 0, because when W is equal to 0, you are going to obtain the same. That means S1 will be equal to S2. Okay, so but S1 is not equal to S2. The solutions are conjugate. Okay, so this is what that means. So the natural response is then written as xn of t equal to exponential the real value here. Okay, for some of you are familiar with linear differential equations, all of these are easy stuff. Okay, so you have exponential the real part of the solution, k1 exponential jwt, where w is the complex part of the solution. Okay, so jwt plus k2 exponential minus jwt. This is another important term that you have to pay attention to, because we'll be dealing with questions like this too. Okay, so for a circuit with purely real element laws and sources, xn is real as well. K1 and K2 have to be complex conjugates. In that particular case, what you can do is when you can say xn equal to k1 exponential jwt plus k1 exponential minus jwt. What are we talking about here? Okay, where with purely real element laws and sources, xn is real as well in that particular case. What we are saying here is that we have a situation whereby k1 and k2 are the same. Okay, that's what we are talking about. K1 and k2 are the same. Okay, so if we have that kind of situation, you see you have, let's k2 be equal to k1, let them be the same. So you can see we have k1 here and we have k1 here. All right, so if you have that, what you can do is you can have 2re. This is how to represent it. 2re, where re represent real, you can call that real. Okay, re represent real. Okay, so you can say 2 real k1. All right, exponential jwt, then we have e, the real term here multiplied by t. Okay, so if you have, if you have it like this, according to some mathematical explanations, some of you are familiar with the Euler's identity and constants and so on and so forth. Okay, if you replace this ejwt here, according to Euler, that says ejwt is equal to cos wt plus j sine wt, is that you know that we have a natural response, which is this, and then if we have a situation where k1 is equal to kt, we can have this can be transformed into this particular equation. These are just the two important things in this particular case here. Please pay attention to this. You will find out that we still have beta 1 here, and then we have beta 2 exponential gamma t, and then we have replaced the exponential terms with the trigonometric terms. Okay, so these are the only things that change. When the real term is 0, it simply means that there is no decay. Okay, when the real term is 0, it means there is no decay. Don't forget, I told you that whenever we solve the simultaneous equation, whenever we solve the quadratic expressions that we obtain from the natural response, we get something like this. Okay, so where this is the complex term and this is the real term. So when the real terms are zeros, okay, when the real term is 0 in the underdamped case, what happens? Okay, let me quickly show you what will happen when the real terms are 0. Okay, it simply means there is no decay, and this usually occurs when zeta is equal to 0. Okay, when zeta is equal to 0, and that is the undamped case I mentioned to you the other time. When the zeta is equal to 0, the real part of that solution will be equal to 0. Gamma will be equal to 0. And this case is the constant amplitude sinusoid with frequency W equal to W naught, hence W naught is called the undamped frequency. Only get your undamped frequency when zeta is 0, and then this real term here is equal to 0. That leads you to being able to find your undamped frequency. This is very important for you. You should pay attention to it so you don't get confused when terms like this are used in problems. Okay. So the third case is a critically damped case. The critically damped case, and that is the case where your zeta is equal to 1. Okay, when zeta is equal to 1, this simply means that you have real and equal roots when you solve the quadratic expression, the quadratic equation that you obtained during the natural response. Okay, don't forget, we are still talking about natural response. We have not even started talking about the forced response at all, just the natural response. Okay, so when you solve the quadratic expression and then you obtain S1 equal to S2, real and equal roots. Okay, this is exactly how to represent those. This is also not a strange thing to some of you who are familiar with your mathematics, differential equations, and so on and so forth. So you see that the natural response in this case will be equal to K1 exponential gamma t plus K2 exponential gamma t. Okay, these exponential terms are the same. So because you have the same solutions, they are the same here. But what you do is you introduce a t here when you have real and equal roots. Okay, you introduce a t here. This t is what just differentiates this two, and then this k1 and k2 terms. All right, so pay attention to that. And then how do we then look at the parallel circuit natural response? Okay, so if the storage element, all the elements in the circuit, RLC circuit, if all the elements in the RLC circuit are connected in parallel, how do we deal with that kind of a circuit? How do we analyze such a circuit? How do we find the solution to the natural response to such a circuit? Okay, after we have done with the parallel situation, we are also going to look at what happens when all the elements in the RLC circuit are connected in series. How do we find the total response, total natural response, to such a circuit? Okay, we're going to look at both scenarios together right now. Okay, so let's begin with the parallel. Let's begin with the parallel RLC circuit natural response. Okay, so if they are connected in parallel, okay, so what you want to do is you take KCL, you find your KCL. Okay, that means that the sum of all the currents around the particular node will be equal to zero. Sum of all currents at the particular node will be equal to zero. So whatever is coming in plus whatever is going out will be equal to zero. What you can see here, this entire stuff here can be treated as a node. This entire stuff here can be treated as a node, okay, because there are no, underlying elements here in between here. So you can treat this entire line here as a node. If you have that, it simply means that what is going in is here, what is coming out is here, and then this is also going out. Okay, that is what it simply means. Okay, so if you are treating these entire stuff as a node, you can say that we have something coming to here. This is your V, and then if it's treated as a node, it simply means you have something is going out here, something is going out here, something is going out here. This could be your L, this could be your R, and then this could be your C, your RLC. Okay, so I just want to show you this so you can know what is going on here. Okay, so if you have that, what is coming in, the current coming in is going to be IG, so this is going to be minus IG. All right, so you have minus IG. Okay, so and that minus IG is what it took to the other side here to give us our plot, to give us IG here. All right, so you have minus IG is what is going in. So everything that is coming out is going to be plus. All right, so you add every other thing together, minus IG equals zero. Okay, so the minus IG is just what we have on the opposite side here. So let's start with the R. The current passing through R will be minus 0 over R. So I passing through R will be equal to V over R. Okay, using Ohm's law. The current passing through L will be 1 over L V dt plus the charge when time is 0. Okay, so you have that here. This is current passing through that, because this is going to be the initial charge before you start charging the circuit. This is going to be the initial charge before you start charging the circuit. Okay, so and since we have a current source here, the initial charge will be in terms of the current here. Okay, so please pay attention to that. This is very, very important for you guys. Plus the current passing through C, I will be equal to C dV dt. The current passing through here will be equal to C dV dt. So add all of this together, minus, because they are leaving the node, minus what is going into the node, minus IG, or you can just say equal to IG, because you would have written minus IG equals 0. But taking IG to the opposite side, it just becomes plus IG. If you differentiate what we have here, so brush up with mathematics, if you differentiate what we have here, this is what you're going to obtain. Now, since we are dealing with the second order circuit, what you want to do is to remove all the coefficients of the second order here. Okay, the coefficient here is C. Okay, so divide everything by C, so that this can be on its own, and then you can rearrange your terms. You can rearrange the terms. So when you do that, you have the squared dt squared plus 1 over R C dt plus 1 over L C d equal 1 over C di dt. Again, if you assume that your characteristic equation If you want to find the characteristic equation or homogeneous equation, you can say that let the natural response Vn be equal to k exponential st, could be the natural response. So if you put these in here and you do all the you do all the substitutions and differentiations, this is what is going to be left, equal to 0. Under normal circumstances, this will also be equal to 0, but then we don't need this because this cannot be equal to 0. Okay, so we have s squared plus 1 over rc, s plus 1 over lc equal to 0. Okay, so this is very, very important. And then when you look at what we have here, what you will find out is that the undamped natural frequency of the parallel RLC circuit, which is W naught here, okay, you don't forget that we said that this is supposed to be equal to square root of A naught right from the beginning, if you remember properly. Okay, this is supposed to be equal to square root of A naught. If you compare these with S squared plus 2 multiplied by zeta, if you remember, we talk about this zeta multiplied by W naught, okay, s, then plus w naught squared equal to 0. Okay, so if you compare these two together, okay, you remember that our w naught will be equal to a squared. We compare this to s squared, plus what did we have then? We had a1, yeah, a1s, then plus a naught equal to 0. When we compared both of them, we got w naught equal to square root of a naught. In this particular case, you can just say w naught squared is equal to 1 over LC straight up. Okay, so you don't have to memorize it. It's just a w naught squared equal to 1 over LC, and then your 2 zeta w naught will be equal to 1 over RC, which is exactly what we do have here. All right. If you do that and then you rearrange, make some mathematical rearrangement, W naught will be equal to 1 over square root of LC, and then your zeta parallel, okay, your zeta parallel will then be equal to 1 over 2r square root of L over C. Keep those two somewhere because along the line you may want to use them to deal with some problems. Okay, so in this particular case, we have looked at some scenarios where we have zeta parallel. This is called critical damping situation. All right, the two real exponents are the same. In this particular case, the two real exponents are the same. Okay, so that simply means in the situation where the gamma 1 equal to gamma 2, that is what we do have here. All right, then we also have a situation where zeta is greater than 1. Okay, so we have two real distinct solutions, and then a situation where the zeta is less than 1. When zeta is less than 1, we have characteristic exponents, complex equations, or complex solutions rather. We have complex solutions. And then if you have this, you can just rearrange these and have zeta minus 1 less than 0. Because this is an equality sign, you cannot just say zeta p minus 1 equal to 0. You have to be zeta p squared. Okay, because this is an inequality term. Right? So pay attention to that. All right, critical parallel resistance can be found by using this. How did we obtain this? Critical parallel can be found by using resistance can be found by using this, because in the critical situation zeta p equal to 1. So in this particular case, if you say zeta p is equal to 1, it simply means that 1 over 2r then square root L over C equal to 1. All right, if you do that and then make R the subject of the formula, this is what you are going to obtain. Okay, that's that. So now what we have here is an example where you see us solving a real example, not just something that is abstract. Let's try to solve a real example and then see how all of these explanations play out. Okay. All right. So what you will find out here is this. We have a circuit here. You can see we have the resistor with a resistance of 5.3 ohms. We have the inductor with an inductance of 2 Henry. We have the capacitor with capacitance of 1/10 farad. And then we have our current source. Okay. So in that situation, from the question says ignore the current source for now, since we're looking for the natural response. If you are looking for the natural response, what the first thing you do is to kill all the independent sources in the circuit. Don't forget, we have not started talking about the first response at all. We're just talking about the natural response. So the first thing you want to do is to kill all the independent sources. So if you kill this, it simply means this is ID will be equal to zero. Okay, you open the circuit, ID will be equal to zero, and then you just have an open circuit voltage, which is one of the things we're looking for right now. All right. So the initial conditions given will be V of 0 minus before the switch is turned equal to 4 volts. IL of 0 minus equal to 0 amperes. Find V of t for t greater than 0. All right. Don't forget I told you for the second order differential, the second order circuit, you must be given two initial conditions. So these are the two initial conditions here for this particular question. All right. Let's take it a step further. What you find out here is that from the previous explanations we gave, you want to apply KCL. Okay, you want to apply KCL, and then you say summation of all the currents going in and out. So if you apply that, what you obtain is the V squared to T squared plus 1 over RC divided T plus 1 over LCV equal to 1 over C D I did the T. Okay, so if you flip back, that is what you see when you're trying to find when we found our KCL. This is what we obtained. If you remember here, okay, this is it here. So applying that here now, this is what we have. So applying KCL is what we have, and now we have real values. So plugging in the values gives us the squared dVdt plus 6 dVdt. Okay, our R, what is our R? 5 over 3. Our C is 1 over 10. Okay, so 5 over 3 times divided by 5 over 3 multiplied by 1 over 10 will give us 1 over 6. If you put 1 over 6 here as RC, eventually it becomes 6. Okay, mathematically speaking. So you have the squared dVdt squared plus 6 dVdt plus what is our LC? If you multiply C and L together, okay, this also becomes 1 over 5. Okay, mathematically speaking, 1 over 5, 1 divided by 1 over 5 becomes 5. So you have 5D here. This will be equal to 0 because ID is 0. So everything here is going to be 0 since we're dealing with natural response. And this source has been killed. So this will be equal to 0. Okay, so once we have that, it becomes what next? This is just a test to show you that zeta must be equal to 0. Zeta parallel is expected to be greater than 1. Okay, so zeta p will be equal to a1 over 2 root a naught. Right, in this particular case, what is our a1? Our a1 is 6. To put 6 here, 2 in 6 gives us 3. A square root of a naught. Okay, what is our a naught? A naught is going to be equal to 5. This is 5 here, so you put 5 here. Okay, so eventually when you find the value of this, it's going to be greater than 1. So CP or zeta parallel is greater than 1. And don't forget, when the zeta parallel is greater than 1, we have an overdamped situation. All right, so we have an overdamped situation when zeta is greater than 1. So the characteristic equation for here for this particular second order circuit becomes s squared plus 6s. All right, plus 5 equal to 0. You know how we get this. So when you solve this, you obtain s plus 1 plus s plus 5 equal to 0. So s1 will be minus 1, s2 will be minus 5. Two real distinct solutions. Since we have first response and second response, our V will be the summation of the natural first response with the natural second response. Okay, so we do have k1 exponential minus t, that is minus 1 times t, plus k2 exponential minus 5t here. So this gives us the summation of the natural response in this particular circuit. But then don't forget that we have initial conditions, and we can use our initial conditions to find the value of k1 and k2. Okay, so how do we do that? How do we use our initial conditions to find the value of k1 and k2? So what we do here is this. Using the principle of continuity on the capacitor, V0 plus equal to V0 minus, and this would also be equal to V of 0, by the way. All right, and that will be equal to 4, as we can see here. That will be equal to 4. All right. Then using the principle of continuity too for the second condition, we're given IL of 0 equal to IL of 0 minus this would also be equal to I of 0. This will be the same thing as I naught, and this would also be the same thing as V naught, representing our initial condition. If you have these KCL when T is 0 plus, okay, as you can see, you have 3 over 5V plus IL plus 1 over 10 dV dt equal to 0. Okay, so the question you want to ask yourself is where did this come from? Okay, current leaving this particular node here, if you take KCL, current leaving this node will be I equal to V over R. Okay, so our V is here, that is how we got V here. Over R, our R is 5 over 3. So you have V divided by 5 over 3, and that would mean 3V over 5. That is how they got this 3V over 5 here. Alright, and then the current passing through to Henry is IL. The current through this inductor is IL. The current through the capacitor is going to be C divided T. Okay, it's going to be equal to C divided T. Okay, current passing through the voltage is going to 3 over V, 3 over 5 V. Current passing through the inductor will be IL. So you have IL here. The current passing through the capacitor will be C divided T. C is equal to 1 over 10 divided T, and that will be equal to 0 because I of J here is 0. Okay, so if you rearrange what we have here and then make some substitution, first of all, we know that our V at 0 at T equal to 0 plus will be equal to 4, initial condition. So instead of writing V here, you put 4 here. IL will be equal to 0 because we've been told that our IL for initial condition will be equal to 0. So you have 0 here, and then you have 1 over 10 divided T at T equal to 0 plus. Here, everything is equal to 0. So when you do that, and you make divinity subject of the formula, because that's the only unknown we have here right now. So your divinity at T equal to 0 plus will be equal to minus 24 volts per second. All right. So you keep this somewhere because we are going to make use. We're going to make use of it. You just keep this somewhere. All right. Then the second conditions to solve for K1 and K2 in the voltage function. Since we have our divinity here, so how do we find our K1 and K2? You notice that we know V equal to K1 exponential minus T plus K2 exponential minus 5T. All right. So in this particular case, when T is equal to 0, our V here is equal to 4. So you replace 4, V with 4 here, and then you have your K1, okay, you have your K1 exponential minus 0 because T is 0, okay, at T equal to 0, V is 4. So you have exponential 0, so it just becomes K1 here, plus, this is going to be equal to that way, plus K2 exponential 0 plus K2 here too. Okay, so eventually you have K1 plus K2 equal to 4. Also, in this particular scenario, divinity at T equal to 0 plus, don't forget, we can differentiate these two, okay? You differentiate these. So when you differentiate these, what would it give you? You would obtain minus K1 exponential minus T minus 5K2 exponential minus T, all right? Which will be equal to dV dt. When you differentiate these, it becomes divinity equal to all of these. And we know our divinity already is equal to minus 24. So it just becomes minus 24 equal to what we obtained here. It will be equal to minus K1 minus 5K2, and then you equate it to 24. Okay, so this is exactly what you're going to obtain. When you do this, you have two equations already. Solve those two equations simultaneously. You obtain K2 is 5, and then K1 is minus 1. Once you obtain that, you bring it right into this particular situation, and then you have your V will be equal to 5 exponential minus T minus exponential minus T. Don't forget that right from this particular point, we had completed our work, but we needed to find the value of K1 and K2, and that's why we had to introduce the initial conditions and then travel this particular path. So don't let this confuse you at all. Right from when we got here, we got the natural response already, but we needed to find the value of K1, find the value of K2. So we had to introduce the initial conditions given, and then we did all of those to obtain K1 is equal to minus 1, K2 equal to 5, and you have to follow these concepts here. Once you do that, you put it right in this back into this equation to find your natural response at the end of the day. All right. Now we have completed discussions on the parallel RLC circuit. Okay, let's quickly look at series RLC circuit. If we have a series RLC circuit, it simply means all the elements, resistance, the resistor, the inductor, and then the capacitor are connected in series, and this is what we have. If we have this, we can easily take our KVL here. You have our voltage source. So taking the KVL, you can see that the voltage across resistance will be, this resistance will be equal to IR using Ohm's law. So you have IR here. The voltage across the capacitor will be equal to 1 over C, I of t dt plus VC of t naught. This is going to be the initial charge in the circuit because we have voltage source here, so it's going to be initial charge in the circuit, plus the voltage across the inductor will be L di dt. Okay, that is how we get, this is the voltage across the inductor, and then minus V of G, which is the voltage source. Okay, so instead of writing minus V of G equal to 0, we just equate, just take minus V of G to the other side, and then we have V of G here. All right, so when you take the KVL, this is what you have. When you differentiate these and you divide by L, this is what you are going to obtain. For the RLC circuit, don't forget we differentiated and divided by C because we had 1 over C as the the term. We had C as the term, the coefficient of the squared, V the T squared. Okay, but this case we had L as a coefficient here, so we divided everything by L to make sure that we have G squared I T squared, the second order term alone without any coefficient behind it. Okay, so we divide that and then we rearrange. So if you do that, what you have is this, and then you can say that for the natural response, okay, this entire stuff is going to be 0. If you equate this to 0, you find S squared plus R over LS plus 1 over LC equal to 0. Okay. So once you have these here, the story remains the same. W naught equal to square root of A naught, which will be equal to square root of 1 over LC, and then your zeta series, okay, will be equal to A1 over 2 square root of A naught, okay, which will be equal to 1 over B. So this is just basic rearrangement in mathematics. If you use the concept I taught you, in the previous discussion a couple of minutes ago. Okay, so you have this in the previous class. So when you have this, critical series resistance can be found by equating this to 1, okay, because this will be equal to 1. Okay, so when you do that, you can find critical series resistance, your RCS, which will be equal to 2 square root L over C. And then for R greater than RCS, your zeta is greater than 1, which is going to be the overdamped case. And for the underdamped case, you're going to have your zeta less than 1, and your R will be less than the R critical series. Okay, so I mean, these are just thoughts that we've talked about. Okay, we're just applying them, in different form. Okay, so these also can be taken to a situation where we use real numbers. Okay, so when you use real numbers, this is what we're going to have. When you use real numbers, L equal to 1, C equal to 1 over 4 in this particular circuit here. Okay, so you're going to have this expression. We are not given R, so we keep R here. Okay, so and then this becomes 4I. What we have here is going to be 1 over LC. This is R over L. Where is it? Okay, here, this is where we are. So we have 1 over LC, and then we have R over L di dt. Okay, so if you put all of those here, our L is 1, so R over 1 is just going to remain R. Here we have 1 over LC here, so multiplied by I. Our LC will be equal to 1 over 4. So 1 over 4 gives us 4. So you have 4I here. You equate it to 0 because we're dealing with the natural response. Okay, so the characteristics equation here will be S squared plus RS plus 4 equal to 0. Using this particular analysis that we've been talking about, W naught, which is natural response frequency, will be equal to 1 over square root of LC, which will be equal to LC is 1 over 4. Okay, so 1 over square root of 1 over 4 will give us 1 over 2. So 1 over 2 will give us 2. Okay, so we have the frequency will be equal to 2 radians per second here. All right, and then again you will find out that zeta then will be equal to R over 4. From what you can see here, you will find out that we discussed 4 cases. We discussed the critical damped case, the overdamped case, the underdamped case, and then the undamped case. We discussed all of those. Okay, so and the reason we had to go ahead to discuss these cases is because when you look at the question we do not have a value of r. So the characteristic equation we obtained is s squared plus rs plus 4 equal to 0. So since we didn't know the value of r, we would have to look at all the 4 possible cases we can have, and then we can easily, assume what r could be, and then whatever we assume r to be for each of those 4 cases will give us an idea of what the responses would be at the end of the day. All right. For the critically damped case, we said that zeta, which is this symbol we have here, has to be equal to 1 for critically damped case. Okay, so if zeta is equal to 1, it simply means that if you put, don't forget that we obtain zeta equal to r over 4 from our expression here. Don't forget that. So if we say zeta is equal to 1 for critically damped case, that means r over 4 will be equal to 1. So r will be equal to 4 in that particular case. That's how we got this r equal to 4. Also, for the overdamped case, we have already said that zeta has to be greater than 1 for overdamped situation. Zeta has to be greater than 1 for overdamped situation. That simply means if zeta is greater than 1, that means that our r over 4 must be greater than 1, because zeta is equal to r over 4. Okay, so that simply means if r over 4 is greater than 1, it will mean r over 4, r will be greater than 4. If you cross multiply, it means r will be greater than 4. So you just pick any arbitrary value that is greater than 4. The easiest one to pick for us here is 5. You could pick 6, you could pick 7, you could pick 8. You could pick any value, any r, as long as it is greater than 4. Okay, so here we pick r equal to 5, because 5 is greater than 4. For the underdamped case, zeta has to be less than 1 for underdamped case. Okay, so it simply means that r over 4 too has to be less than 1, because zeta is equal to r over 4. So in that case, r will be less than 4 in that particular case. In this case, our r will be less than 4. So you pick any value that is less than 4. In this case, r is greater than 4. And in this case, r equal to 4. So in critically damped case, r equal to 4. Over damped case, r greater than 4. So for undamped case, r has to be less than 4. So you pick any value that is less than 4. So you could pick 3, you could pick 2, you could pick 1. All right. So pick whatever is convenient for you, that works for you. In this case, we chose r equal to 2 because 2 is less than 4. At the end of the day, whatever number you choose, that is convenient for you, you will still get to the final, the analysis would be the same at the end of the day. And then for the undamped case, zeta has to be equal to 0 for the undamped case. So if zeta is equal to 0, r over 4 must be equal to 0. Okay, so if r over 4 equals 0, it simply means r, if you cross multiply, r will be equal to 4 times 0. So r will just be equal to 0. Okay, so these are the 4 cases we consider. And you can see we have 4 different r's. So the next thing we do is just put the 4 different r's here at, interval. So first of all, we say let r be equal to 4. You put 4 here. If you do that, what are you going to obtain? I'm going to show you very quickly right now. This is what you're going to have if you do that. You will have x squared. You will have x squared plus 4s plus 4 equal to 0. So if you have these, that simply means you can go ahead and solve this quadratic equation. Once you solve it, you would obtain s equal to minus 2. That would mean that your gamma is equal to minus 2. Okay, you will have s1 equal to minus 2, s2 equal to minus 2, because you will find 2 solutions. So those are real and identical roots. When you have real and identical roots, this is how you're going to solve it based on our previous discussion. Okay, so the first root, you put it k1 exponential minus 2t plus the second root k2. Because they are identical roots, you have to multiply the second expression by t. Okay, it has to be t multiplied. So you have k1 exponential minus 2t plus k2t exponential minus 2t. Okay, because the powers of the exponent must be the same since they have real and identical roots. All right. So that's what happened in the first case, which is the critically damped case. This is going to be a natural response. All right. What happens in the overdamped case, where we said our r will be equal to 5? If r equal to 5, you can just put 5 here, and then you obtain this quadratic equation. So with this quadratic equation, if you solve it, you obtain s1 equal to minus 4, s2 equal to minus 1. These are real roots, and then they are distinct roots. Okay. So our natural response in the circuit would be in equal to k1 exponential minus t here representing s1, s2 equal to minus 1. So you put minus 1 here. And then here you have K2 exponential minus 4t. This represents when S is equal to minus 4, you put that here. Okay, so you have this expression, this response when your R is equal to 5. Also, in the case where we have zeta less than 1, we said our R would be equal to 2. All right, in this particular case, you just put R here. When you do that, what you will find out is you obtain complex conjugate roots. Okay, so that simply means that you obtain the same roots, but then just what you have in the middle here will be different. Okay, they're going to be complex roots, but conjugate because the sign here is different. Okay, one just has plus, one has minus. This is what you have, and as you can see here from our previous discussion, this is the standard form of writing the natural response to complex conjugate roots. Okay, you can see you have k1 exponential minus t here because this value is going to be the real number we have here, which is the gamma we have. It's going to be the real number of the root. It's minus 1 times t. That's why we have minus t here. And the same thing is also happening here too. Then cos, the trig function, then you have cos of square root of 3. Okay, so you can see here, this square root of 3 is from the complex part of the root. Okay, so you have square root of 3, then you have t here. The same thing goes here. You can see we have cos and then we have sine here. Okay, so for the underdamped case, this is exactly how you get the natural response. All right, now for the last one where we have the undamped case, in this particular case we said that our R would be equal to 0. Okay, so when R is equal to 0, it simply means that you put 0 here. All you're going to have left is going to be x squared plus 4 equal to 0. If you do that, okay, that's what we have here. And then your S1 will be J2, S2 will be minus J2. These are the complex part of the root called the imaginary roots. Okay, so you can see that there are no real parts, just complex parts, J2, and when J2 and minus J2. And when you have that, this is exactly how to interpret that mathematically. This is what the response would look like. K1 cos 2t plus K2 sine 2t. This would mean that the real part of the root would be 0. Okay, so and if you put 0 here, it's the same thing as the underdamped case though, but if you just put 0 here, it becomes 1 times k. 1 just gives us 1. Okay, so that's exactly what we have. It just gives us k1. That's why we just have k1 here. So the exponent part is just what disappears from here because the real root for the undamped case, okay, the real part of the root is 0. All right, so these are the 4 scenarios we have in the situation where you are faced with a question and you don't know the value of R. If we had known the value of our R, we would have immediately decided if it is a critically damped case or overdamped case or underdamped or undamped case, and then we just deal with that situation and then we'll move on. But here we have to do a lot of tests to know if R belongs to any of these category of cases, what would it look like? Again, we're going to stop here because we don't have initial conditions for this particular problem. If we had been given initial conditions, then we have the responsibility to find K1 and K2 so we can complete this particular solution. But we do not have initial conditions for this particular problem, so we'll leave the answers just the way they are. All right, so let's take it a bit further. If you come here, you can sketch each of these graphs, each of the 4 cases that we have. Okay, we have the overdamped, critically damped, underdamped, and undamped cases. Okay, so for the current, different values of t starting from 0. Okay, so if you pick your t time from 0 and you keep substituting it into those current responses we obtain up until your current is equal to 0. If you keep doing that, you will find out that you will get this kind of graphs for the current time graph for each of those cases. Okay, so you can just pay attention to that, or you can just try these at your own convenience and see exactly how it plays out. So you can further crystallize your understanding on this. All right, let's take it a step further. So now we want to quickly talk about first response. Okay, let's quickly talk about first response. First response. All along, we've talked about the natural response, and we've been able to do a lot regarding that. So now we want to focus on the first response. The method is similar to the first order circuit. Okay, don't forget, now we're talking about second order circuit. So in the first order circuit, we had talked about natural response and first response all through the first order circuit. So for the second order, the response is also going to look like what we experienced in the first order circuit. So the differential equation we're going to have, this is what it's going to look like. It's going to look like this, as you can see here. And then this is going to be the first term, all right? So the first response is that identified through the general linear combination of f of t and all of its derivatives. In the first order circuit, we assume that the first term would be constant. So if the first term is going to be constant, we kept saying let the response, okay, let the IF response, I first, or first solution be equal to A, because we assume the first term is going to be a constant. So the solution is going to be constant, all right? So that's what we did in the first order circuits, okay? But in the second order circuit, we do not know if the first term would be constant or not. It could be constant, it could be a function that is not constant. It could be a linear function. It could be a trigonometric function. It could be an exponential function. It could be anything, all right? So it could even be a quadratic function, okay? So in that particular case, how do we deal with the first term here? So if f of t is a constant, e.g. an independent source, use a trial force solution that is a constant. So the trial force solution would be A, that is a constant, all right? So that is if f of t is a constant, all right? Now, this is what was done in the first order circuit, like I explained to you guys. So what then happens if f of t is not constant? These are the various variations that you can have. So when it is constant, you assume the trial force solution will be A. When it is a linear function, you assume the trial force solution will be AT plus B. This is a linear term. This looks like saying AX plus B, okay? So this is like our linear, expression, all right? When it is Tn, this is more like a quadratic expression, okay? So if you remember your calculation expression such as AX squared plus BX plus C, that is what this is going to be. So for example, if n is 2, then you have a quadratic expression. This is exactly what you're going to use. If n is equal to 2, it's going to be quadratic. If n is equal to 3, and then you just keep reducing, just keep going like that. So then if the first term is not constant, if it's not linear, if it's not quadratic, let's say, if it's not polynomial, let's say it is exponential in nature, okay? You know this already. You will assume that it is A, the first term, we assume it is A exponential st. This is how to do this. We already did this before. And then if it is trigonometric function, this is exactly how you treat A sin wt plus B cos wt if it is trigonometric function of either sine or cos. It could be sine, it could be cos. Whatever it is, you assume the trial force solution to be, the combination of these. Okay, so it is important for you to pay attention to this so that it will be easier for us to solve as many problems that needs to be solved as time rolls by. All right. I think there is one more point we need to take note of here, which you already know, but it's important I mention it. There are times when trial force solution matches a term in the natural solution. So if this happens, you have to multiply the trial force solution by t. If you have a natural solution and then you have a force solution that is equal to the natural solution or equal to one of the terms in the natural solution, you have to multiply the trial force solution by t, so that you just don't have two same solutions. Okay, so we've talked about this, so we'll look at how to apply that if need be. Otherwise, I will assume you know it. All right, here's an example we can look at together. We have first response example here, and what we're looking for is I2. How do we find I2 in this particular case? First of all, you can see that we have two meshes here, and those two meshes have, one of the meshes have I1, the other one has I2. All right, and as you can see here, we have voltage source. Because we have voltage source here, our response to this particular circuit would be current. It would be in terms of current. Okay, so if we have had a current source here, our response will be in terms of voltage. We've discussed all of this before. Okay, so let's go ahead. So in this particular case, what you can see here, once you have taken the mesh equations, you know what to do. But I'm just going to show you how to take the mesh equations, and then the rest will be mathematics, and then we'll get through these as fast as we can. All right. Look at what is going on here. The mesh equations here would be minus BG, all right? So, we have we have minus bg. We'll start with minus bg. All right, so if you do that, you go on, what is going to be the current passing through 8? It's going to be plus 8i1, right? Isn't it? Plus 8i1, you have that. And then the current passing through 2 Henry is going to be i1 too. So the voltage across 2 Henry would just be L di dt. That's what the voltage is. So it's going to be plus L, which is 2, then the I dt. Okay, so that's how they got to the I dt here. All right, then we also have current passing through 4 ohms would be plus 4 into bracket, because current coming here is I1. You know that, right, from our previous analysis and discussion. Current also passing through 4 ohms. I2 is also passing through it, going up. I1 is coming, flowing down. I2 is flowing up. So you have I2 here. All right. So that means current through these 4 ohms will be 4 into bracket I1 minus I2. Okay. So everything has to be equal to 0. Okay. That's 4 into bracket I1 minus I2. If we do that, what you would find out is, by expanding this bracket and adding and subtracting and rearranging, you will end up with 8i1 plus 4i1. That will give us 12i1 minus 4i2 here. If you take minus Vg to the other end of 0, you obtain Vg, and that becomes the equation 1. This is pretty straightforward for all of us, I will believe, because we are experts in dealing with this stuff. So we've been working on this for a while now. So this is how we got equation 1. Now, for the second loop, what happens? How do we get our equation for the second loop? What you do is, the second loop, you do know that we have current passing through 4 ohms will be 4 into bracket I2 minus I1. You know that already. Okay, so 4 into bracket I2 minus I1, because I2 is going up, I1 is coming down, and with respect to the second mesh, it's going to be I2 minus I1. Current passing through the inductor will be I2, so the voltage induced in this inductor will just be L, it will be plus L di dt. L di dt, our L is 1, so it's just going to be plus 1 multiplied by di dt. Okay, 1 multiplied by the I dt, and then everything has to be equal to 0. So if you expand this, what you have is 4i2. That's how we got this plus 4i2 here, plus the I2 the t. I2, I is going to be I2, so you can put I2 here. So you have 1 times the I2 the t is just going to give us the I2 the t, is how they got what we have here. And then the last one is 4 times minus I1 here will give us this minus 4i1 here. Everything will be equated to 0. Once you do that, all you need to do is just rearrange, and the rest is just mathematics. Just add and subtract and do some mathematical manipulations. If you do that, what you would obtain is that I1 would be equal to 1 over 4. I1 would be equal to 1 over 4 into bracket the I2 the t plus 4i2. If you rearrange these, that's what you're going to obtain, okay, mathematically speaking. So that becomes your equation 2. The question you want to be going to ask yourself is, why did we make I1 subject of the formula? Why didn't we make I2 subject of the formula? What we are trying to do is to write, since we are looking for I2, we have to write equation 1 in terms of I2. Okay, you can see we have I2 here, we have I1 here, we have I1 here. So we're just trying to solve these and then try to write equation 1 in terms of I2, so we can have our standard, circuit equation, second order circuit equation. Okay, so, and when you're writing this, you don't want to write it in terms of I1, because what we're looking for is I2. So it makes sense, naturally speaking, to just make I1 subject of the formula, write I1 in terms of I2, and then replace all I1s in the first equation, and then with that equation that has I2, and then you can then have your final equation. Okay, so that's what we tried, what we're doing here. That's what we're doing here right now. All right, so we did that, and then you put I1 into this particular expression, and then you can see If you do that, this is what you are going to obtain. Okay, and then after you have substituted I1, you don't forget that there is I1 here, so you can only substitute into this particular I1. You can't substitute into this I1 directly here. Okay, if you do that, it's going to be clumsy. You will do it eventually, but the easiest way to do it is to differentiate this I1, because this is the I1 dt. This is the I1 dt here. Okay, we have I1. To find the I1 dt, you just differentiate your I1. So differentiating this I1, you will obtain something like this when you differentiate I1. This is just simple mathematics, differential equations. Okay, so differentiate that and then you obtain this. Once you differentiate that and obtain this, that simply means you can easily then replace this, the I1 dt you have here, with what you obtain after the differentiation of I. All right, so you don't put these two expressions in equation 1, and then when you do that, this is what you come up with when you do that. So everything right on top of this equation is a bit of circuit analysis and then more of differential equations. Okay, so brush up your differential equations in case you're forgetting. This is important for you. All right, let's go ahead. So when you have this kind of equation, what do you do next? So we can assume that Vg is constant. So if we assume that Vg is constant, we can say Vg is equal to 16. Okay, in many questions you will be told what to do. You will be explained, you would have an idea of what your Vg is. You would be told if you're going to be given a question like this. Okay, but for the sake of explanation and then your understanding, we're assuming that the forcing term here is constant. So to make it constant, let's just make Vg 16. 16 times 2 will give us 32. Okay, so if you do that, you come up with this particular expression. Once you come up with this, it simply means you can find both your natural solution and find your trial first solution. How do you find the natural solution? You equate everything we have here to 0 to find the natural solution. So when you do that, you obtain your characteristic equation. This will give you s squared plus 10s plus 16 equal 0. You solve that, you get s1 is minus 2, you get s2 is minus 8. These are real and distinct roots. When you have that, your I natural response will be equal to k1 exponential minus 2t. S1 is minus 2, so this becomes minus 2t here. S2 is minus 8, this becomes minus 8 here as a power of the exponent here. And then you have your k1, you have your k2, and then you have your natural response put together that way. Okay, what would be the first solution? What would be the first solution? The reason you have I2 here is because we're looking for I2, by the way, so we made it I2 natural. If we were to be looking for I1, it becomes I1 natural or I1n. So because we're looking for I2, so we made it I2 natural. How do you get the first solution? That is also pretty easy, okay, because we dealt with this when we're dealing with the first order circuit. How do you find the first solution? That means you're going to equate you're going to say, since this is a constant, all right, since we have assumed that Vg is constant and this is a constant, it simply means that your first solution or I2f will be equal to A, like we usually do and explained before. So it will be equal to A. If it's equal to A, you put A here. Okay, so if you do that, the squared A dt will be equal to 0, the A dt will be equal to 0, everything here will be equal to 0. You'll be left with 16A equal to 32. So your A will be equal to 2 at the end of the day. So if A is equal to 2, it simply means your total solution, which is I2 that we're looking for, will be the addition of the natural solution plus the trial first solution, the natural response plus the trial first response, the solution. That gives us I2n that you see here plus I2f, all right? And that will be k1 exponential minus 2t plus k2 exponential minus 2t plus our 2, which is the first solution that we obtained. So what you will notice here is if you have chosen your Vg to be any other value like 30, like 12, if you are choosing your Vg to be 12, it means you're going to have 12 times 2, 2 Vg becomes 24. So that means you will just have a situation where your 16 ampere equal to 24 and your A will be 32 over 24, and then that's what you would obtain here. So I don't want you to bother too much about why did we choose Vg as 16, why not 12, why not 20, why not 30, why not 100. This is just for the purpose of the explanation and your understanding, because we knew this would be eventually 16 ampere equal to something, and we wanted something that would divide perfectly well. So that's that about this particular situation. What about a situation when we are looking for total response for first series RLC? Total response for first series RLC. In this particular case, what you will find out here is that we have been given initial conditions. You know, in the previous example, we do not have initial conditions. So let me show you. In the previous example, there were no initial conditions, so we didn't have to find K1 and find K2. If we had been given initial conditions, then we'll be mandated to find K1 and K2 and then find the final solution with regards to those details provided. So in this case, we have the initial condition, so that means we'll take it a step further, and these parameters are connected in series, so we're dealing with series RLC circuit. So you can see you have your C, you can see you have your capacitor representing the C, you can see you have your inductor representing the L, you can see you have your 5 ohms there representing the resistance. Okay, so what you can see here, you can see we have the voltage here, and what you would notice here is that our voltage here, you will find out that this doesn't look like a constant term, right? So, but then let's go ahead. I'm going to tell you how to deal with these as mentioned earlier. So you take a KVL from this particular circuit. If you take a KVL along this mesh or this loop here, you find out that the current here, the flow of current here, let's say it's I. Okay, so KVL, you will start by saying you have minus 2e, 2 exponential minus 2t is what you're going to obtain. If you have that, then it's going to become plus 5i, because you know the voltage according to Ohm's law across this 5 ohms will be 5i, IR, that is 5 multiplied by I. And then voltage across this inductor will just be L di dt. So L is 1, so it just becomes 1 multiplied by the I dt, and which naturally give us just the I dt. Okay, if you have that like that. So, and then the voltage across this capacitor will be plus V will be equal to 1 over C, by the way. So you have 1 all over C integral of from 0 to T here, because if you're moving from 0 to T, that means we're going to have an initial charge somewhere. Okay, and since our voltage, what we're dealing with in this circuit is voltage source, so we're going to have an initial charge of VC of 0, which of 0 here simply means that it's an initial charge before the charge. Okay, so but this becomes I of t dt, if you still remember our analysis when we're working, then plus our V C of 0, the initial charge before the circuit is switched on, or before the switch is on, everything equal to 0. That's what we're gonna have here. So if we have this, and if you rearrange this is exactly what we are going to obtain as our KVL. If you rearrange this expression we have right below here, this is what you're going to obtain. You take minus 2e exponential minus 2t to the other side, so you have, it becomes 2e exponential minus 2t. You have your V of 0 somewhere here. You have your 1 over C becomes 1 over 1 over 4. Our capacitance is 1 over 4. So 1 over 4 automatically gives us 4. That is why you have 4 here, just outside the integral value, and then you have your 5i. All right. So this gives us the this equation here. So with this particular equation, if you differentiate it and rearrange it, what would you have? This is what you're going to obtain as your final system equation. You're going to obtain 5 the IDT if you differentiate this. Okay, if you differentiate this, it's going to become minus 2 times 2, it give you minus 4 exponential minus 2t. You know how we got this. Okay, so, and you also know how we got this already. All right, so what else again? If you differentiate the IDT, that means you differentiate, it becomes the IDT dot d IDT. So it becomes the squared I dt squared. You know how we got that. So if you integrate this, you're going to obtain I. This is I the t. Okay, so it becomes I. And then if you differentiate that, if you differentiate the integral of this, okay, it's just going to cancel out. So you're just going to have I left. So I multiplied by 4 will give us 4 I. All right, so this becomes a system equation, and then once we have the system equation, the rest becomes very, very easy. Okay, as discussed in the first in some of the discussions we've had in the past, you will find out that we can go ahead and say here, for the characteristic equation, it simply means that we are going to say this becomes s squared, isn't it? If you still remember. And this becomes 5s, and this becomes just 4. So you have s squared plus 5s plus 4 equal to 0. You solve those, you obtain your s equal to -1, and s will be equal to -1 here, and then s will be equal to -4 here. Those are real and distinct roots, two real and distinct roots. So the natural response at that particular point would be equal to k1 exponential minus t, representing the root s equal to -1, and then k2 exponential minus 4t, power of exponent representing the root s equal to -4. Okay, and then you have a natural response here. Okay, for the first solution, what you will find out here is that this is not a constant, so we cannot assume a first solution of constant. Normally, if it were to be a constant, we'll say let the trial first solution be equal to a. So if would be a. But in this case, it is not a constant, so it is an exponent. Okay, so in this case, what we use for the exponent I give you in the previous table we discussed is going to be a exponential minus 2t, because what we have here is minus 2t. So the trial solution will be a exponential. Don't forget this minus 2t here. It's not just a exponential minus t. A exponential minus 2t. What we do have here, you're going to include it, except it, and then just put a behind it. Yeah, okay, so that's what we have as a trial first solution. In that particular case, if you substitute these into this particular system equation, what would you have? You have d squared I dt squared. If I is a exponential minus t minus 2t, and you put that here, what would we have? It becomes minus. I think I need to break this down for you so you don't get confused at all. Because this, you're going to differentiate it twice. If you do that, there are going to be some cancellations going on there. If you do that, what you're going to have is, so what you find out here is that you differentiate this a exponential minus 2t twice, because this is the square. If you differentiate it once, the first thing you're going to have is, if you differentiate it once, is going to be minus 2a exponential minus 2t if you differentiate it once, right? Then since it is d squared I dt squared, that means you're going to differentiate it again. If you do that again, what you're going to have is 4. So you have 4. What you're going to have is 4. If you differentiate it, a, you're going to have 4a exponential minus 2t. That is what this is going to be. So this is going to be this here. All right, then plus 5 the I dt. If you differentiate it once, it becomes 5 the I. 5, this is the I dt naturally. So 5 times this gives us minus. Automatically, this becomes minus now. So it becomes minus the I dt. It becomes minus 5 minus 10 times minus 2 now. That's 5 times minus 2. It becomes minus 10. All right, minus 10a. Okay, exponential minus 2t. I hope you are following. That's this. So this is gonna be this, and then you have 4i, then plus 4. What is our I? Our I is just a exponential minus 2t, so it becomes plus 4a plus 4a, right? Exponential minus 2t. Everything will be equal to minus 4 exponential minus 2t, isn't it? Everything will be equal to minus 4 exponential minus 2t. Okay, minus 4 exponential minus 2t. Okay, I hope you can see. So what you will find out here is that we have 4a exponential minus 2t. If you add that to this, it gives you 8a exponential minus 2t. 8a exponential minus 2t minus 10a exponential minus 2t will give you minus 2a exponential minus 2t. That's what it will give you. All right, so that means we have taken care of everything here. Everything here will give us minus 2a exponential minus 2t, which will then be equal to minus 4 exponential minus 2t. Okay, so that is exactly how they got what we have here. So if you understand what I've done so far, it becomes pretty easy for you. So that is exactly how they got this value that you're looking at here, what you're looking at here is exactly the same thing as what we just got here. So I just had to show you how they got that. Okay, so if you do that, it simply means this is going to cancel out this. You have minus 2a equal to minus 4, and then your a will be equal to 2 at the end of the day. Okay, so this is simple mathematics, and then I think it's something that you will be able to deal with. So a is equal to 2. If a is equal to 2, that simply means your total solution will be the natural response plus the forced response, or the trial forced solution, and that will give you I equal to in plus if. Our in is k1 exponential minus t plus k2 exponential minus 4t. You can see here, plus a is 2, it will not be plus 2 exponential minus 2t. Okay, it's not just 2, it's not just plus 2, it's plus 2 exponential minus 2t. Okay, this becomes the total solution. Okay, but in this case, we will not stop here. Why? Because we have been given initial conditions. So when you have initial conditions, you want to go ahead and find the value of k1 and the value of k2. So you can only do that by applying the initial conditions. Okay, when you do that, you will find out that your k1 is equal to 1, and then your k2 will be equal to minus 2. You just apply the same concept, and then you will be able to obtain your k1 equal to 1, k2 equal to minus 2. If you put those in this particular expression, your final solution will be called exponential minus t, as you can see here, because k1 is 1, minus 2, k2 is minus 2, becomes minus 2 exponential minus 4t, then plus 2 exponential minus 2t ampere. This becomes your total response. All right, this becomes the final solution with those initial conditions.